Can everyone hear me? Okay, thank you for that introduction. So the question that I'm going to explore with you this evening is what happens when teratonnes of carbon dioxide are emitted to the atmosphere? I think this is a relevant question. There's a lot of dialogue today about what future Earth will look like. The current interglacial cycle in which we live today is relatively cool, and it's anomalous in a long time perspective. So up to 70% of the time in Earth's history, the climate's been in a greenhouse state where temperatures have been much warmer. Climate models suggest that if we continue to emit carbon dioxide to the atmosphere, the Earth will re-enter this relatively stable greenhouse state, and due to positive feedbacks, will stay there. So I'd like to know, what would such a greenhouse climate look like? And what would it look like to live there? So to do this, we can use geology. We can look to the past as an analog. And today I'm going to take you back in time to about 145 to 65 million years ago. And this is called the Cretaceous period. At this time, carbon dioxide levels were 6 to 10 times higher than they are today. And surface air temperature was 12 degrees Celsius higher than today. And there was no polar ice. So to examine past climates and environments, we can turn to the rock record. And this is a photo of one of my field camps in 2017 in the Canadian Arctic. And you can see our tiny little tents there. And the rock record has lots of clues. It can tell us about past changes in the carbon cycle, which I'll show you today, and how environments responded to these changes. And I'll show you that today as well. Now, Leonardo also knew that the rock record contained a lot of information about the history of life on Earth and the history of the planet. And he is quoted as saying, "We know more about the stars high above our heads as about Earth just below our feet." So how does teratonnes of carbon dioxide become emitted to the atmosphere in geological history? One way is when the mantle of the Earth is emitted to the surface of the planet. And there's a variety of mechanisms by which this can happen. But when that hot magma rises, it interacts with sedimentary rocks. If those sedimentary rocks contain coal, or indeed even hydrocarbons in sedimentary basins, that carbon is mobilized into the atmosphere. Now, one such way is called a mantle plume. These are thin thermal diapirs of magma that rise from the mantle to the surface of the Earth. When these cool on the surface, they form what is known as a large igneous province. So to meet this criteria, it has to be enough magma emplaced over a short amount of time. 100,000 kilometers cubed of magma emplaced in 1 million years or less. These mantle plumes and large igneous provinces are implicated in almost every mass extinction in the history of life on Earth. One way in which scientists believe that these cause mass extinctions is through the release of carbon dioxide to the atmosphere. The quantity that can be released is anywhere between 20,000 gigatons to over 100,000 gigatons. So how much carbon is that? So to place this number in the context of the current dialogue on climate change, humans released 10 gigatons in 1960 from the combustion of fossil fuels. And that number has steadily increased to about 37 gigatons in the year 2017. So the United Nations Paris Agreement seeks to keep global warming to 2 degrees Celsius, or preferably less, above pre-industrial temperatures. So carbon budgets have now been calculated. We have about 1,000 gigatons left to emit, and that budget will be used up in about 27 years. So we know that carbon, when it's emitted, is partitioned into various carbon sinks in the atmosphere and in the ocean. And we need to know more about those sinks. And so looking in the geological record to past carbon cycle perturbations can tell us about carbon sources and carbon sinks and Earth system response to the release of massive quantities of carbon dioxide. So I'm going to show you today an example. We're going to go to the Canadian Arctic, where I've worked for about the past 10 years. And there's a sedimentary basin there. It's called the Sverdrup Basin. And we're going to go to Axel Heiberg Island, which is where the star is here, to a locality called Glacier Fjord. Now, in this locality, a mantle plume occurred, and it caused the high Arctic large igneous province. And you can see the black line running across that rock outcrop. That's one of the many sills of this magma that came up to near the surface in this case, and then went along the bedding plane. And those rocks that it went into have high amounts of carbon. So the high Arctic large igneous province mobilized a lot of carbon dioxide. Estimates from the Barents Sea alone suggest that 20 teratonnes of carbon were mobilized. This is equivalent to 175 trillion barrels of oil combusted and released to the atmosphere. And this was sufficient to perturb the global carbon cycle. So the data I'm showing you here today is a lithostratigraphic log, so geologists think in terms of time on the y-axis. And the data is carbon-13 to carbon-12 relative to a standard. So this is called delta carbon-13 or carbon isotope stratigraphy. And you can see the large negative excursion at the bottom of the record. This is due to the release of massive quantities of carbon dioxide. And it was sufficient enough to stimulate global warming, probably by about 3 to 4 degrees Celsius. What that did is it stimulated massive productivity in the world's oceans. When those organisms died, they degraded, and that degradation used up almost all of the oxygen in the world's ocean. That led to an ocean anoxic event, and there's a number of these that occur throughout the Cretaceous interval. That carbon drawdown from the atmosphere to organisms and then buried in the marine reservoir actually then caused global cooling. The ocean is one of the modulators of the climate system. And these ocean anoxic events appear to end the extreme hothouse crises by taking the carbon dioxide out of the atmosphere into organisms and buried in the sediments. And studying ancient greenhouse states offers us one of the best means for predicting the Earth response to future warming. Now, I talked about global cooling events. This photo here is of a mineral. It's called the glendonite, and it's one of the ways that we know these transient cooling events occurred following or during the ocean anoxic events. It's thought to only occur when marine conditions are near freezing. So I brought a sample with me today. Every geologist always has rocks. So please come and see me at the reception, and you can see this. I collected this from the Glacier Fjord locality myself, and it's about 120 million years old. So further up in the rock record at Glacier Fjord, we see these events happening again. Again, there's carbon cycle perturbations, and this is associated with the large igneous province. Again, there's ocean anoxia, and again, there's transient cooling. So I also want to look at the terrestrial record. So we know that peatlands, soils, and forests are important in the global carbon cycle. And there's something really interesting about polar regions during the Cretaceous. At this time, an extinct polar biome existed. The Antarctic and Arctic regions were covered with cedar-like forests. This is a photo of an in situ tree stump here. It's of a species called metasequoia, which would be similar to dawn redwood. And I took this photo on Ellesmere Island in the Canadian Arctic. And in the background is vast landscape covered with these stumps. And this is a remnant of that extinct polar biome that persisted in Arctic regions, despite the high northern latitude, for up to 100 million years. And so I wanted to know, how were these ecosystems affected by these climate changes? So to do that, I collected rocks from the Glacier Fjord locality, and then I looked under a microscope at all of the pollen and spores contained within them. And that offers a means to see what the vegetation was and how it changed. So here, plotted stratigraphically, so again, time is on the y-axis, is how the percentage of fern spores and tree pollen have changed. And what you can see is there's a spike in the ferns, in fern spores. And this so-called fern spore spike is considered a disaster indicator. Fern spore spikes occur coincident with almost every mass extinction since the evolution of land plants. So the high Arctic large igneous province and associated perturbations to the carbon cycle affected marine ecosystems globally, and it affected these polar forests. So in summary, the Cretaceous period was a time interval that experienced extreme environmental change, and this was associated with volcanism-related carbon dioxide emissions. These triggered extreme global warming. This was followed by low oxygen conditions in global oceans, ultimately due to the drawdown of carbon dioxide from the atmosphere into marine sediments. These cold snaps ended the extreme hothouse climate conditions, and the planet then returned to a stable greenhouse state. The scale of these temperature changes were about 3 to 10 degrees Celsius. I read a news article today before coming here that shows that climate models suggest that global temperatures will increase by about 4 degrees Celsius by the end of the century. So this is within the same magnitude as we're seeing in the rock record. So I hope I've shown you today that observations made using chemistry, biology, and geology can permit connections and improved understanding of Earth system response. Careful observations are something that anyone can do. The only requirement is curiosity. I'd like to end with an interesting story that illustrates the power of observation. The rock record is often featured in Da Vinci's works, and there are 2 versions of Da Vinci's Virgin of the Rocks that I show here. The first is in the Louvre, and the second is in the National Gallery of London. There's debate as to whether Leonardo painted the National Gallery version. So far, research on the 2 works have centered upon an analysis of historical documents. Anne Pisa-Russo is a geologist who has studied Leonardo's paintings and drawings from a geological perspective. The Virgin of the Rocks illustrates the shaping force of water that Leonardo da Vinci knew was important in forming the surface of the Earth. The walls of the large cavern in the surrounding scene are eroded, and in the background is the clue as to this erosion, as a large river flowing from the horizon into the cavern. Leonardo's attention to accuracy and detail of geological formations can be used to authenticate his work. I'd like to end with the quote from the geologist Anne Pisa-Russo, who says, "The difference in the 2 sets of rocks in the paintings may not be immediately obvious, yet given Leonardo's passion for geology, genius for painting, closer evaluation suggests that the Louvre rocks are Leonardo's and the National Galleries are not. Leonardo's observational geology is far more accurate than the geology of Renaissance theorists. Such extraordinary knowledge provides us with an unbiased method to distinguish his work from that of his many imitators and followers. Precise geology is an index to authenticity, and it can serve as Leonardo's trademark." Thank you very much for your attention.